My name is Bhavya Balu, and I'm a PhD student working with Professor Aditya Kher at Carnegie Mellon University. And today I'm going to be talking about particle motion in asymmetric rectified electric fields that are these steady electric fields generated when an oscillating or AC voltage is applied across an electrolyte. Now, AC voltages applied across electrolytes occur in a lot of different applications, but the one I'm going to focus on today is that of colloidal particles assembling under AC voltage. So people have found that when you apply an AC voltage across a suspension of colloidal particles in an electrolyte, these colloidal particles form these planar assemblies or aggregates parallel to the electrode. Now, this can further be exploited in various different applications, such as coatings technologies and electronic displays. The images here are from experiments from Dennis Prevy's group, where on the left is the colloidal suspension of polystyrene beads in sodium bicarbonate when there's no applied electric field. And on the right is what happens when you apply an electric field for a few seconds. You can see these planar structures that are created under this electric field. They've done this experiment for various different electrolytes and various different electric fields. And a lot of different groups have worked on this, but I want to show you experiments from one particular group that found some interesting results. So this is experiments from Bill Ristenpad's group at UC Davis, where they look at similar systems of colloidal particles near an electrode and how they respond under this applied electric field. So what they see here on the left is a schematic of their experimental setup, where they have an electrode at the bottom and a colloidal suspension on top. And when you apply a time-dependent voltage on this electrode, they see a similar response of colloidal particles aggregating near the planar surface of the electrode. What they also find is this kind of strange behavior of some of these colloids that float or levitate at a certain height away from the electrode. The image on the right is the same thing, but in the microscopic form, where they have these planar structures, planar aggregates of colloids shown in green, and these floating colloids shown in red. Now, the fact that the colloids floated or levitated was interesting because the height at which they were levitating was much larger than most typical length scales in any of these colloidal systems. And so the question was, why do some of these colloidal particles aggregate near the surface, whereas some of them levitate or float? So the reason or the explanation for this was also put forth by the same group a couple of years later, and they did that using numerical simulations, where they discovered that when you apply an oscillating electric field across an electrolyte, you're able to generate a steady electric field in the electrolyte. Now, this is kind of remarkable because what they're saying is when you apply a voltage, which is oscillating in time, such that it has a zero average in time, you're able to generate a steady non-zero electric field in the electrolyte. So that raises a question of what really is causing a zero average input to produce a non-zero average output, and what are the physical reasons for this? Additionally, they claim that this steady electric field is long range. And so then we want to ask the question, what exactly is this long range of the electric field, and can we predict it and figure out what physical parameters does it depend upon? And so they actually go ahead and answer a lot of these questions, but they do that using full numerical simulations. And numerical simulations in these electrochemical systems are inherently pretty hard to do for reasons I'll get into in a little bit. But to answer a question such as what is the long range of this electric field, they had to do a large number of computationally intensive numerical simulations to get this answer. So our goal here is to come up with an analytical or theoretical formulation of the steady electric field that would then enable us to answer such questions in a much more simpler fashion. And additionally, we also want to think about what the steady field means for colloidal systems and how would colloidal particles move in the steady electric field. So to do this, I want to first talk about physically what happens in an electrolyte when you apply an oscillating voltage across it. And then we'll go over the mathematical description. So the way I study the system is by using a model electrochemical cell that has parallel electrodes and an electrolyte in between. The electrolyte has positive and negative ions. And when there's no applied voltage, the ions are uniformly distributed. Now, once you apply a voltage, the electrodes get charged, and the ions in the electrolyte move towards oppositely charged electrodes, and they form these diffuse layers of charge in front of each electrode. Now, since the applied voltage is oscillating, it means that, let's say, the electrode on the right here goes from being positive to 0 to negative and then back again. So in response to that, the ions in the electrolyte also keep moving back and forth between oppositely charged electrodes. Now I want to introduce a layer of complexity, which is that of asymmetry. So particularly, we want to consider the asymmetry in the diffusion coefficients of the ions. That is, the positive and negative ions have different diffusion coefficients, and they move at slightly different rates. So under an oscillating voltage, what this means is that these positive and negative ions are moving back and forth between the two oppositely charged electrodes, but they're doing that at slightly different rates. And it turns out this is actually what causes a steady electric field to be generated. So the asymmetry in diffusion coefficients is the physical reason for which, due to which a steady electric field is generated under an oscillating voltage. Now let's look at what is the mathematical description of this system, and how do we come up with an analytical expression for the steady electric field. To do that, I look at the ion transport equations, which are like Poisson-Nernst Planck equations, which are species balance equations and electric potential balances for the charge density, the ionic strength, and the electric potential in the system. So the species balances are conservation equations for the charge density rho and the ionic strength C. On the left-hand side, we have time-dependent terms, which describes the rate of change of the species with respect to time. And these are balanced by the fluxes. So you have a diffusive flux because of concentration gradients, but additionally, unique to electrochemical systems, we also have this electric migration flux, which describes how these charged species move under an electric potential. Now, a couple of things I want to point out about these species balance equations. First is that the time-dependent terms have a coefficient alpha, which is the dimensionless frequency of the system. Additionally, they also have this coefficient beta, which is an asymmetry parameter, which quantifies the difference in diffusivities of the two ions. Now, if the two ions had equal diffusion coefficients, beta would be 0, and the time dependencies would simplify quite a bit. The other thing I want to point out is that this electric migration term is nonlinear. And so this gives you, like, this kind of hints at the answer to how a 0 average input voltage is able to produce a non-zero average output electric field. And well, that's because the system is inherently nonlinear. Apart from the species balances, we also have an electric potential balance, which balances the charge density in the system against the electric potential phi. This is basically Gauss law for electrostatics, but in differential form. Here, what's important is this ratio 1/kappa L, which is the ratio of the thickness of this diffuse layer of charge in front of the electrode to the length of the cell. In most typical systems, this ratio is really small. For example, the diffuse layers are usually about a few nanometers thick, whereas like typical microfluidic cells are at least a few microns thick. And so this ratio is at least, or is lesser than 1/1000. So this actually makes it really hard for numerical simulations of these systems, because now you have to resolve your domain over these two very different length scales. But for our theoretical analysis, this actually is advantageous, and I'm going to quickly show you how we take advantage of this small ratio. So again, what we're saying here is that this ratio 1/kappa L is really small. So the electric potential balance can basically be transformed to this form where the charge density is 0 outside the diffuse layers. Now, this greatly simplifies the species balance equations, and because the charge density is 0, we only now have the concentration gradients and the electric potential gradients. Here, I want to point out that we're not completely ignoring the diffuse layers, but instead, we are saying that we are separating the solutions of the diffuse layers from the bulk, and the diffuse layers affect the bulk through the boundary conditions. Now, the remaining species balance equations are still nonlinear because of this electric migration term. And so to proceed, we use perturbation expansions. Particularly, we use weakly nonlinear perturbations to still capture the nonlinear effect that is a steady electric field. Now, without going into too much more detail, I want to start talking about some of our main results. The main result we have is the analytical description of the electric field. So I'm going to show you that and then also talk about what this means for particle motion in these systems. So here is the expression for the leading order steady electric field as a function of the position x in the cell. So this is leading order, so it depends on the square of the applied voltage. And there are higher order terms which we haven't calculated yet. So one thing I want to point out is this entire steady electric field depends on this parameter beta, or is multiplied by this parameter beta, which is the asymmetry parameter. So once again, if the two ions had equal diffusion coefficients, then beta would be 0 and you would not get an electric field at all. But in most realistic cases, beta is almost always non-zero. And so in general, you would expect the steady electric field in most systems. The other thing I want to point out is that we now know the functional dependence on the position. And so from this, we're able to get a characteristic length scale or range of the steady electric field. So from our expression, we're able to get that the range of this steady field is inversely proportional to the square root of the frequency. And so if you wanted to increase the range of this electric field, you would want to decrease the frequency and vice versa. Now, these are like just some things you can just directly see by looking at the expression. So now we want to think of what does particle motion actually look like in these systems. So let's take a look of a plot of the electric field on the y-axis with the position on the x-axis. And this plot is particularly for hydrogen chloride. So here beta, the asymmetry parameter, is around 0.6. For the electric field is non-monotonous. And so it becomes positive and then negative and then positive again and goes through 0 multiple times. So now the question is, what does a particle do in this electric field? So let's consider the region on the left of this plot where the electric field is positive. And so a positively charged particle will tend to move towards the right. That is in the positive x direction. Now, similarly, if you look at the right end of this plot, again, the electric field is positive, and so a positively charged particle will want to move towards the right. Now, if you look at the region in between these two, the electric field is negative, and so a positively charged particle will want to move in the negative x direction or to the left. So now consider this point, which is the colored black square, where in any vicinity of the point, a positively charged particle will want to move towards this point. So we call this point an attractor or a stable point. Conversely, if you look at this open black square, any positively charged particle in the vicinity of this point would want to move away from it. And so we call this an unstable point. So we can kind of naively extend this to the case of multiple colloidal particles, where now you get that any positively charged colloidal particle in the vicinity of this stable point will move to that stable position in X. And so this actually ties back to the initial experiments from Bill Ristenpart's group, where they see colloids levitating at a height much further away from the electrode. And I believe that this stable point is that levitation height. Now, what we also found, though, is that particle motion under an electric field alone does not completely describe particle motion in these systems. And so let's see the reason for that. Let's look at a slightly different plot, which is that of a particle velocity against position. Here, the red line is the electrophoretic velocity, which is particle motion under the electric field E. But in these systems, in addition to an electric field, we also have a concentration gradient. So charged particles in a concentration gradient undergo diffusiophoresis, where the diffusiophoretic velocity is proportional to the gradient of the concentration. And it looks like this gray line on this plot. So as you can see, especially closer to the electrode, the diffusiophoretic velocity and the electrophoretic velocity are comparable. And so the total velocity of the particle is actually quite different from just the electrophoretic velocity. And so we would have to consider particle motion under both electrophoresis and diffusiophoresis to really complete the picture of particle motion in these systems. With this, I'd like to conclude by saying that we derived an asymptotic expression for the steady electric field that is generated when electrolytes are subject to AC voltages. And using this, we predicted what the particle motion in these systems would look like under both an electric field as well as a concentration gradient.